Let's discuss how to solve logarithmic equations. And there are a few different ways of doing it. The first method makes use of the fact that logarithmic functions are one-to-one. One-to-one implies that when the outputs, f of x is equal to f of y, are equal to each other, that implies the inputs, x is equal to y, that is, the inputs are equal to each other. For logarithmic functions, that implies that if log x equals log y, that is because these have the same base, that you can conclude that the arguments are equal, that is x is equal to y, okay? And we're going to use that as our first way for solving logarithmic equations. Let's go ahead and do it. So let's solve natural log, remember this is log base e, of 3x minus 4 plus natural log of 2 equals 2 natural log of x. Okay, now we're trying to get one log on the left and another log on the right. So I see that I have a sum of two logs, and we have a property that says that you can combine these two logs to get the log of the product of the arguments. That is, the left-hand side can be written as natural log of 2 times 3x minus 4, which is 6x minus 8. I'm using the property that natural log of a plus natural log of b equals natural log of the product ab. Okay, and then the right-hand side. Now the right-hand side, remember, we want natural log of something on the left and natural log of something on the right. I don't quite have natural log of something on the right. I have 2 times natural log of something, so I'm going to take that 2 and write it as an exponent. So this becomes natural log of x squared. And you can do that because the second property we have is that natural log of, let's write it as b times natural log of a is equal to natural log of a raised to the b. That is, the coefficient can be used as an exponent of the argument, which is what I did here. So now that the two functions on the left-hand side both have the same log with the same base, and they're equal to each other, now you can set the arguments equal to each other because the natural log function is one-to-one. That is, we get 6x minus 8 is equal to x squared. And then we have to solve that quadratic equation. So x squared minus 6x plus 8 is equal to 0. Factoring, we have x minus 4 times x minus 2 equals 0. So x is equal to 2 or 4. Those would be our solutions. So one thing to be aware of is that if you solve this equation and you get negative numbers, for example, you have to go back and check. So x can't be negative because we're taking the natural log of it, and the domain of a log function is from 0 to infinity. So you have to exclude extraneous solutions if you have numbers here that cause one or more of the expressions in the original equation to be undefined. Okay, let's look at another logarithmic equation. Let's solve 2 take away log of 1 minus x is equal to 3. And this problem is different in the sense that there's only a single log. And when there's only a single log, what you do is you isolate that logarithm. So I'm going to get the log by itself. So I'm first going to subtract 3 from both sides, and I'm going to add log of 1 minus x to both sides. And I'm going to get 2 take away 3 is equal to log of 1 minus x. And then this is going to be negative 1 is equal to log of 1 minus x. And when you have a single log, what you do is you convert it to an exponential equation. Now remember, the base is a 10 because this is a common log. So 10 raised to the negative first equals 1 minus x. So I get 10 to the negative first equals 1 minus x. That's what we mean by convert it to an exponential equation. So the left-hand side is 1/10, and the right-hand side is 1 minus x. So if I solve this equation, I get x is equal to 1 minus a tenth. So x is equal to, it's going to be 9/10. Okay, and that would be our solution. Now I can see, of course, that if I plug in 9/10, 1 take away 9/10 is a positive number. So once again, this does not cause the original expression to be undefined. So it's a valid solution. Okay, finally, sometimes you want to solve logarithmic equations for which there is not an explicit technique like what there was in these previous two problems. So for example, we want to solve this graphically. This is actually an exponential equation, but the same logic applies for logarithmic equations. Not all exponential and logarithmic equations can be solved using techniques that give you an explicit answer. In other words, we don't have techniques for some equations. This is a very common problem that you run into, and the way you handle it is by solving it graphically. So we're going to solve this graphically, and the way you do it is you basically And the same thing would be true with a logarithmic function, is that you get everything on one side and then you set the other side equal to 0. So I have e to the x take away x cubed take away x is equal to 0. And then what you do is you create a function where this is the definition of the function. That is, you're going to let f of x be equal to the function e to the x minus x cubed minus x. Okay. Now, if this is the function, if the function is this, the problem is asking us, hey, when is that function equal to 0? So we want to know, when is this function equal to 0? So we're going to solve it graphically. So we're going to use a computer to graph this, and then we're going to see where the function is 0. That is, we're going to see where it crosses the x-axis, and we're going to round those values to 2 decimal places. Let's go ahead and do that now. Okay, so here I've shifted our screen over, so this is the problem we are working on, and here's our function, e to the x minus x cubed minus x, and we want to know when it's equal to 0. And on the left-hand side, I've graphed the function using a program called Desmos, which is a great online graphing calculator for free. And so what I did is I typed in the function, y equals e to the x, take away x cubed minus x, and here's the graph that I got. And you can see that the places where it's 0, there are 2 decimal approximations. The first one is about 1.37. So our solutions would be x is about equal to 1.37 would be the first one. And the second one, the function would be 0 here, about 4.67. So 4.67. And those would be our solutions. So that would be how you solve an exponential equation graphically. Now you can do the same thing. You can solve a logarithmic equation graphically. So let's go ahead and do that now. So you can't always solve a logarithmic equation explicitly. Sometimes you have to rely upon solving it graphically and looking at your graph and getting the answer and raising the, expressing the answer to a certain number of decimal places. And that's what we're asked to do in this problem. So this is a classic problem where you have a log and then on one side and then some sort of polynomial on the other. So when you have something like this, we don't have any techniques that allow you to solve it like we did in the first 2 problems. So the way we handle this is we get everything on one side of the equation and we write x take away log of 2 take away x squared, and the right hand side is going to be 0. And then we set a function equal to the left hand side of the equation. That is, we say f of x is equal to x take away log of 2 minus x squared. Let me rewrite that. So 2 take away x squared. Okay, and then what you do is you graph this function and you look for where it's equal to 0, right? Because that's what this is saying, hey, when is this 0? But I've defined the function to be that, so now it's going to be the x-intercept of that function. So we're going to graph that using Desmos. Let's go ahead and do that now. That's right, there's 1. Negative 1.4, so our solutions would be x is about equal to negative 1.4 is the first one, and then there's another one right here, so it'd be about 0.283. So let's write 0.28. Now we wanted 2 decimal places, right? So that would actually be negative 1.40. So those would be our solutions.